Okay, last up for section 7.1 is topic 7, which is linear and angular speed. And we do need to do a quick recall of something that we learned in Math 171. So when you're dealing with distance, rate, and time, there is a relationship between the three, and we know that distance is equal to rate times time, or D equals RT. Now, back in 171, we would do these uniform motion problems and we would talk about solving for t. So we knew that if we took this formula and solved for t, we got distance divided by rate. That's great. In this class, we want to look at what happens if we solve for the rate. So if we have distance equals rate times time and we want to solve for the rate, we would divide by t on both sides. So that tells me the rate is equal to the distance divided by time. And that's going to be really, really important when we start looking at linear and angular speed. Okay, so let's go ahead and talk about angular speed. So angular speed tells us how fast our angle is changing. Okay, so basically it's comparing the angle we are changing with time. So the angle that's being swept out compared to some unit of time. Okay, we always denote this with the Greek letter omega. So it looks kind of like a weird curvy W. So that's omega. And what we have is that omega is the ratio of the angle to time. And we're going to denote the angle as being theta in radians, okay? So we get this ratio right here. Omega is equal to theta divided by time. That's that comparison of the angle changing to time, okay? Common units that you would see for angular speed would be degrees per second, radians per second, or perhaps radians per minute. And there is another one. You will sometimes see angular speed as revolutions per minute, so RPM. And that's great. You could be asked to calculate angular speed and represent your answer as revolutions per minute. However, you will oftentimes have to convert revolutions per minute to radians per minute, or revolutions per unit of time to radians per unit of time, okay? Now, linear speed, on the other hand, it tells us how fast our arc length is changing. So compares the arc length with time, so how fast we travel on an arc compared to time, and this is denoted by V, okay? So we have V equals S over T, because remember, S is what we use for arc length. So it's telling us, okay, this arc length is changing compared to time, so it's a ratio of arc length to time. So arc length divided by time, okay? And remember, arc length is R being our radius times theta being the angle in radians, okay? So we have this right here so far. So arc length V is S over T, but S is really R over theta. Okay, and common units for linear speed would be meters per second, miles per hour, feet per second, kilometers per hour. So some kind of length per unit of time. Okay, now we've got a couple of things that we really need to look at and understand. We can kind of see a relationship between linear and angular speed. Okay, so we notice that if we write linear speed as S over T. Well, we know that S is arc length, and we also know that arc length is R times theta. So we could write linear speed as R times theta over T. But notice that this is really R times theta over T. And what is theta over T? Well, that's just your angular speed. So we can say that linear speed is the radius times linear speed. Okay, or angular speed rather. So linear speed is the radius times angular speed, because this right here is omega. Okay, so we will frequently use this. Now, when you're finding linear speed, if your omega, your angular speed, is given to you in revolutions per unit of time, you really do need to convert it to radians per unit of time. Okay, so again, when finding linear speed, omega should be measured in radians per unit of time. If it is given to you as revolutions per unit of time, you need to convert it to radians per unit of time. And in order to do that, remember, one full revolution is equal to 2 pi radians. Okay, so we have these two things, angular speed, linear speed. Not really hard to calculate. It's basically just going to be measurement conversions, just a bunch of dimensional analysis. But I do want you to understand like what is really happening here. So imagine a car. Literally everybody's dream car, okay? When you're talking about linear speed, you're talking about like kind of how fast that car is traveling, okay? So what is the speed of the car? When you're talking about angular speed, you're talking about how fast are the wheels rotating. So this is linear speed. This is angular speed. A lot of people will also talk about Ferris wheels. So when you're talking about Ferris wheels, the angular speed is how are those spokes changing? How fast are those spokes moving? And then the linear speed is how fast is the little bucket moving that you're sitting in, okay? So again, linear speed is kind of how fast the thing is going. Angular speed is how fast are the wheels rotating, okay? So that's kind of the big difference between the two. And don't be jealous of my super sweet ride right here, okay? Now, one last thing I want to caution you about. We're going to be dealing with radians a lot in this class, and it is really helpful to think of a radius as a length per radian. Okay, so we have to kind of remember, what is that definition of a radian? Well, 1 radian is the angle required to create or form an arc that is exactly the same length as the radius. So if we have a circle here, we've got whatever our radius is. And if we imagine that length of the radius, and we can just peel that off and make an arc length that's exactly the same length as the radius. 1 radian is the angle required to do that. So for each radian, you have like a length of 1 radius going around the circle. So we can think of the radius as the length per radian. And that kind of helps you when you're doing these conversions, because there's this hidden radian that a lot of times you have to be like, oh, where's this radian? It's here. So when you're talking about the radius, okay, the radius is a very specific length. If we measure that length and then just pile it around the circle, for each radian, there's a length of 1 radius around the circle, okay? Now let's get into solving. So example 12, we have solve, include units with the answer. So we're either going to be finding linear speed or angular speed. Please remember, linear speed is v, which is really, let's see, linear speed is the radius times omega. Remember that. And then omega is the angle over time. Now, we also had that v equals some distance over time, basically. Okay. So we were, let me just pull it up here because I've already got it written out. Right. So we had some arc length over time, but we said arc length is r over, or is r theta. And so we said, okay, linear speed is s over t being arc length over time, which is really radius times theta over time, which is really radius times theta over time, which that gives us r omega. So remember this. So it was s over t, which is really r theta over t, which is really r times theta over t, which is really r times omega. So we're going to use these two formulas, especially this one. Okay. Now let's look at our examples. So for part A, we have, let me scroll down just a little bit. A child is spinning a rock at the end of a 2-foot rope. They're doing this at a rate of 180 revolutions per minute. So that's your RPM, revolutions per minute. Find the linear speed of the rock when it is released. So kind of envision this. We have a 2-foot rope. We have some rock at the end and some kid is spinning it, okay? When they're spinning it, that rock is basically creating a circle, okay? So we have, let me draw that a little bit better right here. There. Good grief. I hate when Microsoft tries to fix this and make it prettier than I want it. Okay. So we've got a radius of 2 feet. That's the actual length of the rope. And then we're spinning this rock and it's going around and around in a circle. And that 2-foot rope is the radius of that circle. Okay. So what we want to do is find the linear speed. Okay. Now we have to remember, for us, linear speed is the radius times omega. Okay. But I also told you earlier, let me scroll up so you can see it. I said right here, when finding linear speed, remember that omega should be measured in radians per unit of time. If given omega as revolutions per unit of time, we need to convert it. So that's going to be part of our conversion. We were given revolutions per unit of time. We need to convert that to radians, okay? So let's get back down to our problem. So we have linear speed equals r times omega. We know that omega needs to be radians per minute, but they gave us revolutions per minute. So we need to deal with that. So let's go ahead and think about what this is going to look like. So we have V equals, well, we have our radius. We know that's 2 feet. And remember, I told you that it's really helpful to think of the radius as length per radian. Okay? So for each radian, we know that that's an angle that's creating an arc length that's equal to the radius, okay? So when we come down here and we start filling in this formula, we know V equals, V being linear speed, is the radius times omega. Well, we need to write our radius as length per radian, okay? So we have 2 feet, okay, per 1 radian, okay? Now, omega, they gave it to us as revolutions per minute, okay? So we've got 180 revolutions per 1 minute, but we really need to convert that to radians. We want radians per unit of time when we're finding our linear speed, okay? So what we have to remember is when we're talking about 1 full revolution, if we need to convert that to radians, 1 full revolution around a circle is 2 pi radians, okay? So we have 2 pi radians for each revolution. Now, you might be like, how did you get these numbers? Well, let's think about it. We have our radius, which is right here. It's 2 feet, but I told you it's really helpful to think of the radius as length per radian. So for every radian, we have 2 feet for the radius, okay? And then we had our omega, okay, that angular speed was flat out given to us as revolutions per minute. But we need to convert this to a linear speed, which needs to be in dealing with like radians per minute. So I need to convert revolutions to radians. And I need to remember there's 2 pi radians per revolution. Well, we need things to cancel. Okay, we've got radians that need to cancel, and we've got revolutions that need to cancel, right? So we've set this up to where radians are top and bottom, revolutions are top and bottom. So using dimensional analysis, these things are going to cancel, which is really fantastic, okay? So let's see what cancels. Well, we get revolutions to cancel. That's awesome. We get radians to cancel. That's awesome. So now we just have a few things left that we need to simplify. So the linear speed, we have 2 feet. Let's see, we have 180. We have 2 pi. So that's everything that's left in the numerator. The denominator is really just 1 times 1 times 1 minute. So let's see how all of this simplifies, okay? So let's see what we get here. We have 2 feet times 180 times 2 pi over 1 minute. So we probably want to go to the calculator, so make sure you have this written down before I switch screens to the calculator, okay? So I'm going to go to my calculator. I've already told you I don't love my calculator setup, but we use what we have. So we had 2 feet times 180 times 2 pi. And remember, to get to the pi, you hit the second button and then the caret button, which is above the division symbol. And then we hit enter. And we're going to round this. Let's go 1 decimal place. So we get, well, let's just round this to the nearest whole. So we get 2,200 and let's say 62. So let's go to the nearest whole here. So on our worksheet, when we work this out, we get 2,262. Well, 2,262 what? Well, look at the units that are left in our problem. We still had feet and we still had minutes. So this tells me that this rock was swinging around at a rate of 2,262 feet per minute. And that was our linear speed. Okay, so remember, linear speed is some kind of length of an arc per unit of time. So this rock is traveling at 2,262 feet per minute. Okay, now let's look at the next example. So the next example, we're going to be finding angular speed. Okay, so for part B, we have a truck that has a wheel radius of 1.7 feet and it's moving with a linear speed of 35 miles per hour. What is the angular speed of each wheel in radians per second? So remember, I drew that really, really cool car up here. Again, don't be jealous of my sweet ride, okay? So we have this car here. And remember, linear speed is kind of like how fast the car is just going in general. So that would be miles per hour, feet per minute, whatever. What we're looking for is how fast are those wheels rotating? So how fast are those wheels spinning if this car is going 35 miles per hour? So a truck with a wheel radius of 1.7 feet moves with a linear speed of 35 miles per hour. What is the angular speed? Well, let's think about what we have. We know a few things. We're given linear speed. Okay? Linear speed is 35 miles per hour, but we need angular speed. So let's think about what that means. If we have linear speed is r times omega, we could solve this for omega, right? So we could say, okay, if we divide both sides by r, then omega equals linear speed divided by r. Or we could take this one further and we could say this is linear speed times 1 over the radius. So let's think of it like that, okay? So let's go ahead and build this. So we have omega equals v times 1 over r. So let's think about what v is. I already have that written down, so I don't need to write it again. Well, v is 35 miles per hour. That's the linear speed. So we're going to do 35 miles per 1 hour. Now, our goal is to convert this to radians per minute or per second. So we've got some work to do here. So we have basically v. This is v right here. We need to multiply this by 1 over the radius. But remember, when you think of the radius, it's a length per radian. So we're going to write this as 1 radian for a radius of 1.7 feet. Okay, well, that's good so far. So the issue is we have miles and hours, but we need radians and we need seconds. Okay, so that's not so bad. We need to definitely convert miles to feet. And then we also need to convert hours to seconds. We've got our radian. Okay, we've already got a radian in the numerator. So let's focus on miles and feet. You may not remember this, but I'm here to tell you that for every mile, we have 5,280 feet. And notice here, I put miles in the denominator and feet in the numerator because I want the miles to cancel, okay? I'm looking for radians per second. We got to deal with this. We've got that miles cancel. We've got that feet cancel. That's really great. So at this point, we definitely have radians in the numerator, but we still have hours and not seconds in the denominator. So we need to do some converting between hours and seconds, okay? So I know that 1 hour is equal to 60 minutes, but that's not seconds. I happen to know that 1 minute is equal to 60 seconds. So let's think about what else cancels. So now we have a situation where hours cancel. Remember, things cancel top to bottom. Minutes cancel. That's great. So now I have radians in my numerator and I have seconds in my denominator, and that's exactly what we're looking for. We're looking for radians per second. Okay, so let's clean this up. So omega is now, well, for my numerator, I have 35 times 1 times 5,280 times 1, and the unit is radians. In the denominator, I have 1 times 1.7 times 1 times 60 times 60, and the unit in the denominator is seconds. So let's see what this looks like when we simplify it. So make sure you have this written down before I switch screens to the calculator. So when I go to my calculator, I'm going to set up a template for a fraction. I just think it's easier. So to set up that fraction template, I go alpha y equals. And for my numerator, we had 35 times 5,280. And remember, that unit was radians. And then in the denominator, we ended up having 1.7 times 60 times 60, and that unit was, I believe, seconds. So hit enter. And let's round this to like 1 decimal place. So if we round this 1 decimal place, we get 30.2. So let's think about what that means. There we go. So when we simplify, we get 30.2 radians per second. And that gives us our angular speed. So that tells us that these wheels are rotating at a speed of 30.2 radians per second. So that's pretty cool, right? It's really like, even though these are kind of in-depth concepts, linear and angular speed, it's really just dimensional analysis. You're just figuring out what you have and what you need to convert to, okay? I decided at the last minute to throw in one more example. So let's look at example 13. This one says solve, include correct units with the answer. Now, this one is a little wacky. We're finding angular speed, but this time, just for fun, we decided to find it in revolutions per minute, okay? So let's think about what we have. We have a truck has a wheel radius of 1.4 feet and is moving at a linear speed of 45 miles per hour. What is the angular speed of each wheel in RPM, revolutions per minute? Okay, well, we're given the linear speed. But we need angular speed. So let's think about that again. Well, in the last example, we used, okay, the fact that the linear speed is going to be the radius times omega, but we need to find the angular speed. And we know the relationship between linear and angular speed is that linear speed is radius times angular speed, but we want angular speed, not linear speed. So we would divide both sides by r. And that tells me that the angular speed is the linear speed divided by r, or I could think of this as v times 1 over r. And that's what I'm going to use right here. Okay, so omega equals v. What is v? V is the linear speed. So that's how fast this truck is just moving down the road, which is 45 miles per hour. So 45 miles per 1 hour. Now, I need to multiply that by 1 over the radius, but remember, it's not just a regular old 1. When we're thinking of a radius, it's length per radian. So that tells me for each radian, I have a radius of 1.4 feet. And that's really important. You can't just lose that radian, okay? So for each radius, it's 1 radian, okay? Now, we've got a lot of converting to do. We need to find a way to convert this to revolutions per minute, okay? Whoa. Okay, so we have to deal with this radians and revolution situation. We know that 1 revolution is always 2 pi radians. So let's go ahead and deal with that. We need to get rid of radians and convert that to revolutions. So I know for each revolution, it's 2 pi radians. So at this point, if we're canceling stuff, radians have canceled. So that's a good thing, okay? So we now have our revolutions in the numerator. The issue now is we need to deal with like the length that we have. We also need to deal with time. So we need to get converting here. Okay, so we need to find a way to get feet and miles to cancel. So notice we have miles here and we have feet here. So let's think about that. There is a conversion that relates feet and miles. And it just so happens that there are 5,280 feet per 1 mile. So if we're keeping track of what's canceling, we now have a way to cancel miles and we have a way to cancel feet. Okay, so that's really good. But we need revolutions per minute. We've got our revolutions, but we don't have minutes, we have hours. So how do we convert hours to minutes? Well, I know that 1 hour is 60 minutes. So now, again, if we're keeping track of what cancels, hours have canceled and now I've got minutes. So if you look at the remaining units, my numerator has revolutions, my denominator has minutes, and that's exactly what we want, okay? So now we just have to clean this up and simplify. So we now have, whoops, is that gonna convert? There we go. So we have omega equals, well, for my numerator, if I look at just all the numerators, I've got 41 or 45 times 1 times 1 times 5,280 times 1. So I have 45 times 5,280, and that's revolutions. That's the remaining unit. For the denominator, I have 1 times 1.4 times 2 pi times 1 times 60. So that means I've got 1.4 times 2 pi times 60, and the unit that's left in my denominator is minutes. So let's go to the calculator, make sure you have this written down before we scoot over to the calculator. And hopefully you see that we're just doing dimensional analysis. We're just converting a bunch of stuff. That's all that there is to it. All right, so I'm going to do the fraction template again. So I'm going to go alpha y equals and then choose option 1. So for my numerator, let's see, I had 45 times 5,280, and that was revolutions. My denominator, I had 1.4 times 2 pi. Remember, pi is going to be second caret button. And then times 60, and that was minutes. And then we just hit enter. And I'm going to round this to the nearest whole. Let's say it's 450. So we're going to get 450 revolutions per minute. Okay, so when we simplify, this simplifies to approximately 450 revolutions per minute. And there you have it. So 450 RPM is the angular speed of each wheel. And there you have it. So that's linear and angular speed. Hopefully that wasn't too bad. Hopefully the big thing that you notice here is just keep in mind what you start with and the units you need your final answer to be. And all units that you don't need in your final answer need to cancel top to bottom. Okay? So just a bunch of measurement conversions.